Welcome to the late night shift of the deep dive. I'm so glad you're here with us. Settle in, grab your coffee, or maybe that third energy drink of the day.
Or fourth, depending on the sprint cycle.
Right, the fourth. Tonight, we are doing something highly specific. We are looking directly at you, the software engineer, the person who spends their days deep in IDEs, wrangling APIs, and maybe wondering how all these massive AI models actually tick under the hood.
Because you know how to build complex systems, right? You understand logic, state management, data pipelines.
Exactly.
Yeah.
But there is a fascinating, almost jarring shift happening in how we engineer intelligence right now. And tonight, we're going to trace the exact moment that shift happened.
It really is a profound transition. I mean, to understand the massive large language models dominating the landscape today, you have to understand the bridge that got us here.
Yeah.
We're diving into the precursors to modern transformers, specifically the sequence-to-sequence architecture, usually abbreviated as SEX2.
XUSEC, right.
It's an older architecture by AI standards, but the story of its limitations is exactly what forced the invention of the systems we use today.
Exactly. Our mission tonight is to cross that bridge. We've talked before about the foundational stuff, like word embeddings.
Which are incredible on their own.
They are.
Yeah.
Because they give computers a way to understand individual words by mapping them into a geometric space, meaning literally becomes math. But as anyone who writes code or speaks a language knows, language is not just a bag of isolated words.
No.
Not all language is entirely about sequences. The order changes the meaning entirely.
Yeah.
Think about the string. The dog bit the man versus the man bit the dog.
Same exact words.
Same exact embeddings. But one is a standard news story and the other is a front-page headline.
And that sequence, that specific order of operations, was historically a massive, just seemingly unsolvable headache for computer scientists.
Why was it so bad?
Well, what's fascinating here is that mapping one sequence to another isn't just a quirky linguistic puzzle. It represents a foundational shift in systems engineering. We spent decades trying to brute force human language using traditional programming logic, and it failed spectacularly.
Let's talk about that failure, because it started with a very specific driving problem: machine translation.
Oh yeah, the ultimate test.
The absolute nightmare of getting a machine to turn French into English. For decades, right up until about 2014, the standard approach was rule-based systems. Picture trying to write a parser for human language.
It's painful just thinking about it.
Right. You had rooms full of linguists and programmers painstakingly handcrafting grammar rules and vocabulary mappings. It was basically a giant, infinitely expanding switch statement.
If this, then that.
Exactly. If you see this exact grammatical pattern in French, then apply the syntactic transformation, rearrange the nouns, and substitute these English equivalents.
You can just imagine the technical debt. You simply cannot write enough regular expressions or if-then statements to capture the edge cases, the idioms, the sheer nuance of human language.
It's brittle.
Way too brittle. Eventually, the field realized that explicit logic wasn't going to scale, so they shifted toward statistical approaches. Instead of hand-coding rules, researchers started counting patterns in parallel texts.
Like looking at raw data.
Exactly. They would take massive data sets like the proceedings of the European Parliament or United Nations transcripts, things that are meticulously translated into multiple languages by humans, and they would look for statistical correlations between phrases.
Which, as an engineer, sounds a bit better, right? You're finally letting the data do the work instead of hard-coding the logic.
It was an improvement, certainly, but structurally it was a nightmare to maintain. It relied on incredibly clunky pipelines. You had a separate statistical model for language processing, a separate component for phrase extraction, and another module entirely for word reordering. It was a Frankenstein's monster of different statistical algorithms stitched together into a single pipeline.
And if you've ever maintained a massive microservice architecture where a dozen fragile services have to align perfectly, you know exactly how painful that is.
Oh, absolutely.
If the phrase extractor fails, the word reorderer gets garbage data. What researchers desperately wanted was an end-to-end system. Put your French string in, get your English string out.
Just one black box.
Let one unified neural network handle everything in the middle. But they kept hitting a massive structural roadblock, and it comes down to array lengths.
The dimensionality problem.
Right. Take the phrase, I love cats, 3 words in English. In French, that's j'adore les chats. 4 words.
Right, you cannot just do a simple one-to-one mapping across the arrays. Index 0 to index 0, index 1 to index 1, it breaks down immediately.
It shifts entirely.
The structure of the sentence morphs. Word order shifts based on grammatical gender. A concept that takes one word in English might take three in French, or vice versa. The input sequence length and the output sequence length are completely decoupled.
So how do you actually engineer a system that takes an array of unknown length, processes it, and outputs a different array of a different unknown length?
That disconnect is exactly what the sequence-to-sequence architecture was born to solve. In 2014, two landmark papers dropped almost simultaneously.
From who?
One from a team at Google, including Ilya Sutskever, Oriol Vignoles, and Kwok Lei, and another independently from Kyung-Yoon Cho's group. They introduced an incredibly elegant two-part structure, the encoder and the decoder.
Okay, let's unpack this.
Yeah.
Because this is the core of it.
Let's look at the encoder first. It's usually a recurrent neural network, specifically an LSTM or a GRU. For our software engineering listeners, don't get bogged down in the acronyms. Think of an LSTM as a recursive function that passes its state forward to the next iteration.
So it reads the input string word by word,
Yeah.
right?
Exactly. The encoder reads the entire input sequence, one token at a time. And as it processes each word, it updates its internal hidden state. It is holding on to the context in a continuous vector space.
Building a memory.
Yes. And when it finally hits the period at the end of the sentence, that final hidden state, that dense array of floating point numbers, is the mathematical representation of the entire thought. It compresses the whole sequence into a single, fixed-size vector.
I love the analogy of reading a novel for this.
Yeah.
You sit down, you read hundreds of pages, and then you close the book. You can't recite the text verbatim.
Right, it's a lossy compression.
But you hold the essence of it in your mind, the emotional arc, the plot twists, the characters. That mental state, that compressed understanding, is the final vector produced by the encoder. It has absorbed a sequential array into a single point of data in memory.
That's a great way to visualize it. So now you have this compressed vector, this essence, you hand it over to the second half of the architecture, the decoder.
The generation side.
Exactly. The decoder is also a recurrent neural network, but it operates in generation mode. It takes that single compressed vector, initializes its own starting state with it, and begins generating the output sequence, one single word at a time.
And it loops, right? It looks at what it just generated, combined with that underlying meaning vector to predict the next word. It just keeps firing until it outputs a specific end-of-sequence token.
Precisely. Think of the decoder like a simultaneous translator working at the United Nations. They listen to the speaker's entire statement, that's the encoder phase. They form a complete mental representation of the argument.
And then they start speaking.
Right. They produce the translation word by word. Crucially, every word they choose to say next depends entirely on two things: their deep understanding of the original speech and the specific words they have already chosen to say in their translation so far.
Sequence in, compressed to a vector, sequence out. From an architectural standpoint, it is a beautiful piece of engineering. But practically, how do you train that?
It's tricky.
Because early in training, a neural network is basically just outputting random noise. If the decoder uses its own previous output to predict the next word, wouldn't the errors just cascade?
They absolutely do.
If it spits out garbage at step 1, then step 2 is being predicted based on garbage. It sounds like a game of telephone where every single person in the line is completely drunk. The message would degrade catastrophically with every step.
You've hit on the exact bottleneck of recurrent generation. If you let the model train that way, it will almost never converge. The noise overwhelms the signal too quickly. So researchers implemented a clever training solution called teacher forcing.
Teacher forcing, how does that work?
During the training phase, instead of letting the decoder feed its own messy predictions back into itself, you provide it with the ground truth. You manually feed it the correct previous word from the actual training data.
Oh, that makes total sense. It's a lot like writing unit tests with mock data. Instead of letting a downstream microservice fail because the upstream database gave it malformed garbage, you hard code the mock response. That way, you can actually test the downstream logic in isolation. If I'm learning a complex 10-step recipe and I burn the butter in step 3, the whole dish is ruined. I'm not going to learn how to execute steps 4 through 10 properly because my base is destroyed.
It's unrecoverable.
Right. So teacher forcing is like having a master chef swap my ruined pan for a perfect one so I can practice step 4 under normal conditions. You reset the state to the correct ground truth at every single step.
It's a highly effective technique. Teacher forcing makes the training loop incredibly fast and mathematically stable. But this raises an important question about the transition to production.
There's always a catch.
Always. It introduces a subtle, insidious problem known as exposure bias. Because the model is always given the perfect answer during training, it never learns what to do when it makes a mistake. It is entirely reliant on the safety net.
Right, because when this ships to production, that safety net is gone. During inference, there is no ground truth to feed it. The model is essentially flying blind.
Exactly. It has to rely entirely on its own predictions. If it makes a slight grammatical error early in a sentence, it has no training on how to recover or steer the sentence back on track, because it was never exposed to its own errors during the learning phase.
That is such a classic systems engineering trade-off. You solve the training bottleneck, but you introduce a behavioral quirk in production. And speaking of inference, the way the model actually navigates the probability space to generate text is fascinating.
It's a huge search problem.
Because at each step, the decoder isn't just definitively picking a word, it's assigning a probability score to the entire vocabulary. The naive approach would just be greedy decoding, right? Pick the highest probability word at step 1, then the highest at step 2.
You could do that, but locally optimal choices don't always lead to globally optimal sentences. Greedy decoding is like being dropped in a maze and just walking toward whichever hallway looks brightest at that exact moment.
You might walk straight into a dead end.
Exactly, missing a slight detour that would have taken you directly to the exit. You need a way to look ahead without calculating every possible path, because exhaustive search, calculating the probability of every single possible sentence combination, is computationally impossible.
So greedy search is too narrow, and exhaustive search crashes your server. How do they find the middle ground?
This is where we use beam search. For anyone familiar with tree traversal algorithms, it's essentially a constrained breadth-first search with heuristic pruning. You keep the top K hypotheses alive at every step. That K is your beam width.
So if I set a beam width of, say, 3, am I basically sending 3 independent processes to explore different branches of a decision tree simultaneously?
That's exactly it. You send 3 explorers into the maze. They all take different paths. At the next intersection, you evaluate all their possible next steps, score the new total path probabilities, drop the worst ones, and clone the best explorers to keep probing the most promising branches.
That's brilliant.
And there is a very specific engineering sweet spot here. In translation models, a beam width of 4 to 10 works best.
Wait, why not a beam width of 100? If you have the compute power, wouldn't exploring more paths yield a better sentence?
You would think so, but it actually degrades the output. First, the memory overhead of holding 100 parallel states across a 50-word sentence is massive. But more importantly, making the beam too wide dilutes the signal.
How does it dilute it?
The model starts evaluating so many paths that it ends up favoring incredibly safe, short, generic outputs. There is a Goldilocks zone for exploring the probability space without getting lost in the noise.
If we pull back and look at the bigger picture, all these architectural pieces, the encoder, the decoder, teacher-forcing beam search, they all coalesced into a massive industry-shaking shift in November 2016.
The GNMT launch.
Exactly. That was when Google rolled out the Google Neural Machine Translation System, GNMT. They completely ripped out their old statistical microservice-style pipeline and replaced it with a deep C2-SIC model. And the architecture was heavy. It used 8 layers of stacked LSTMs for both the encoder and decoder.
And the results redefined the field. Overnight, they saw a 60% reduction in translation errors across several major language pairs.
60%.
Think about that from an engineering perspective. 60%. People woke up, typed a phrase into Google Translate, and realized it actually sounded fluent. It was no longer a party trick. It was a genuine utility.
As a software engineer, this is where the story gets incredibly profound. Researchers spent decades, literally entire careers, handcrafting linguistic rules, tuning statistical pipelines, and building complex NLP microservices.
And it was all wiped out.
Within 2 years of those 2014 SIG2SIG papers being published, this end-to-end neural approach rendered all of that obsolete.
If we connect this to the bigger picture, it is a phenomenal, albeit painful, example of what the AI community calls the bitter lesson.
The bitter lesson.
It's the realization that approaches relying on human-engineered knowledge, logic, and handcrafted rules will almost always eventually be beaten by approaches that simply leverage massive computation and generalized learning algorithms.
Butte wins.
Always. For a software engineer, that is a humbling reality. The machine, given enough data and a flexible architecture, learned the underlying rules of human language better than the world's top linguists could explicitly code them.
And it didn't stop at translation. See how text became the ultimate hammer, and suddenly every sequence problem looked like a nail. Think about it. If you have any problem where you need to map one array to another, this architecture fits.
Text summarization.
Exactly. Input a massive string of an article, output a short summary string, same exact architecture, just trained on different data. Dialogue systems, input the user's chat history, output the customer service response. Speech recognition, input audio waveforms, output text.
It was everywhere.
And crucially for the engineers listening tonight, code generation.
Yeah.
Input a natural language prompt like, write a Python script to sort a database, and the model outputs the syntax. SecTest was this beautiful, universal framework.
It was a massive unifying moment in the field. Suddenly, vision researchers, audio engineers, and NLP scientists were all speaking the same architectural language. But as elegant as it was, this architecture had a fatal flaw.
Here's where it gets really interesting.
A structural bottleneck born directly out of its own design.
Because compressing an infinite amount of sequence data into a single fixed-size vector sounds too perfect. There has to be a catch. What happens when the input array is just too long?
The catch is dimensionality. Whether your vector is 256, 512, or even 124 dimensions, it is a fixed container in memory. You are essentially trying to squeeze an ocean into a bottle.
Right.
Think of a court reporter whose job is to summarize an entire day of complex legal testimony, but they are only allowed to write their summary on a single standard index card.
If the testimony is a quick back and forth, did you see the defendant? Yes. The index card is perfectly fine.
Exactly. But if it's 4 hours of intense cross-examination, it is physically impossible. Crucial details are going to be overwritten or omitted entirely. That is exactly what happens to the internal hidden state of the recurrent neural network. It has limited capacity.
It just runs out of space.
Every time the LSTM processes a new word, it performs a matrix multiplication to update the state. By the time it reads word 40, word 41, word 42, the mathematical representation of word number 1 is fading away into a ghostly echo. It's a form of memory decay.
The vanishing gradient problem in action, and researchers saw this clearly in the data, right? Seek-to-sec was absolute magic on short sentences, but once you hit about 20 or 30 words, the translation quality just drove off a cliff. The vector became an absolute bottleneck.
It did, and the engineering workarounds they used to try and bypass this bottleneck showed just how desperate the situation was. One of the most famous hacks was simply reversing the input sequence.
Oh, really?
Yeah. If the English sentence was, "I love cats," they would feed it to the encoder as "cats love I."
That feels like a massive hack. As an engineer, that is so brittle. You're depending on reversing the array order to mask a memory leak, essentially.
It is incredibly brittle, but mathematically, it ensured that the beginning of the sentence was processed last. That meant the start of the sentence was the freshest data in the encoder's memory vector right as the decoder was taking over to generate the beginning of the translation.
That's wild.
The fact that manually reversing the array measurably improved performance proves just how severe the memory decay was. The order of operations was completely dictating the quality of the translation.
But a hack is still a hack. You're still trying to fit a whole book onto an index card. And the reality of translation, or code generation for that matter, is that different parts of the output depend on very different parts of the input.
Exactly.
When you're translating the end of a French sentence, you don't need a vague, glossy summary of the whole English sentence. You specifically need a pointer to the end of the English sentence.
Precisely. Seek-sick fundamentally forces the decoder to work blind. It's like forcing someone to write a highly detailed book report entirely from memory, with the book locked away in a desk drawer. You might get the overarching themes right, but you will fail on the specific quotes and details.
You need to see the source material.
What you actually want is for the writer to keep the book open on their desk and simply look back at the relevant paragraphs as they write each section of the report.
And that desire, the need to open the drawer, take the book out, and look back at the specific, relevant parts of the input sequence. That is the exact teaser for the attention mechanism.
The next big leap.
The realization that we shouldn't force everything into a single bottleneck vector. We should let the decoder look at the entire sequence of hidden states and decide dynamically what to pay attention to at any given moment.
It's important to recognize that seek-sick wasn't a failure because of this bottleneck. It was arguably the most productive limitation in the history of artificial intelligence. It proved that end-to-end learned representations could absolutely obliterate handcrafted logic.
It proved the concept worked.
It brought neural networks out of the lab and into global production systems, serving billions of queries a day. The encoder-decoder framework didn't die, it evolved. The massive language models we interact with today are still conceptually built on encoding sequence meaning and decoding sequence outputs.
So what does this all mean for you, the software engineer listening tonight? We trace the arc from brittle, handcrafted, if-then linguistic pipelines to statistical microservices to a fully end-to-end neural network that learned the complexities of language purely from data.
It's quite a journey.
We saw how the bitter lesson proved that massive computation and learned representations scale infinitely better than human-engineered logic. And we saw how the physical limits of memory states forced the next great leap in architecture.
I want to leave you with a thought to mull over before we sign off. Think about the specific transition we just discussed. Decades of painstakingly handcrafted linguistic rules were replaced in essentially 2 years by an end-to-end neural network that just figured it out from the data.
2 years to wipe out decades of work.
We already know that sequence-to-sequence models can map natural language to code. So as these systems scale, and as attention mechanisms and transformers remove those memory bottlenecks, what happens when they start learning the deep rules of software architecture itself?
That's the real question.
If human-engineered linguistic pipelines became technical debt overnight, are we currently engineering the very tools that will make traditional hand-coded software engineering obsolete?
That is a heavy, fascinating question to end the night on. The bridge from hard-coded rules to learned representations changes everything about how we interact with machines. Thank you for joining us on this deep dive. Whether you're debugging an API, fighting with a memory leak, or building the next great architecture, keep questioning the systems you use. Have a great night, and we'll catch you on the next one.